part 2. If you haven't watched part 1, stop. Go watch part 1. By the end of this presentation, you should be able to identify ammonia as an acid or base and explain how water can act as an acid and a base. Neutralization reactions. So bases neutralize acids, right? They will always produce a salt, this, which is an ionic compound, so any ionic compound, and water. So you're going to have to be able to recognize if a reaction is a neutralization reaction. So here we've got hydrochloric acid, which is an acid. Sodium hydroxide base produces a salt, this is table salt, and a water. Nitric acid, potassium hydroxide will yield water and a salt, and the salt is potassium nitrate. It's an ionic compound, so it's not just table salt, okay, an ionic compound in water. Arrhenius definitions. Okay, so there's two types of acids, Arrhenius and Bronsted-Lowry. The Arrhenius ones are very easy to recognize because they all start with an H, okay, and they produce that when they dissociate and conduct electricity. They all produce hydrogen ions in solution. Bases all produce hydroxide ions. So Arrhenius bases all end in OH. So those are pretty easy to recognize. Now Bronsted-Lowrys are a little more complicated. Acids are hydrogen donors or proton donors. I call them proton donors because basically that's what hydrogen is, just a proton. Bases are hydrogen or proton acceptors. Okay, so the acids are giving away a proton, bases are accepting them. Now when that happens, you're going to produce a conjugate base. So after the acid gives away its proton, it then becomes the conjugate base. After the base has accepted the proton, it becomes the conjugate acid. Okay, here's a little acronym to remember: bases accept, acids donate. So your conjugate base will always be paired with your acid, and your base is always going to have a conjugate acid. Now some compounds like water are amphoteric, meaning they can accept and give protons. Alright, so here are some of the reactions. So this is the generic reaction here. An acid and a base will yield a conjugate acid and a conjugate base. So you see the little arrow here, how it's different? It's two-sided because these equations can go back and forth. So here, the acid is going to donate this proton to this base. So we get H3 plus, H3O plus, it's a hydronium ion. This base has now become the conjugate acid. And after we take away this proton, the acid now becomes the conjugate base, because if this reaction was going to go the opposite way, if it's going to go this way, this now can donate the proton to this base. Okay, so here HCl, this is our acid, plus water is going to be our base. Now look over here, which one of these can donate a proton? Well, this is the one that can. So this is now our conjugate acid, and this is our conjugate base because it can now accept a proton. Down here, this one's a little tricky. Do you see how there's an H here on the end? This is acetic acid. So this is our acid. Water is our base. Not always. Sometimes water could donate a proton, but in this case it is. Now, which one of these has a proton it could donate? This one. So this is our conjugate acid, and this is our conjugate base. Alright, strong or weak acids. You need to know the 7 strong acids, which hydrochloric acid, hydrobromic, hydroiodidic, sulfuric, nitric, and 1, 2, 3, 4, 5. Chloric. Those are the 5. Y'all need to know those 5. And these are the strong bases. Y'all just need to know them. Alright, pH calculations. Grab a calculator, write all these equations down. Alright, practice problems. Vinegar has a pH of 2.82. What is the pOH? Well, I told you in your equations that pH plus POH equals 14. So if I subtract 2.82 from 14, I will get 11.18, which is my POH. What is the concentration of hydroxide ions? Well, from that list of equations I gave you, hydroxide ion equals 10 to the negative POH. So 10 to the negative 11.18 gives you 6.61 times 10 to the negative 12. That's my OH concentration. Okay. All right, let's talk about sig figs real quick. Since this is my POH, anything after the decimal counts. Anything before the decimal doesn't count. So here we only have 2 sig figs. So my final answer needs to be in 2 sig figs. So 6.60. Remember, this 0 doesn't count in regular sig figs. Alright, so this is 2 sig figs. This is 2 sig figs. It's complicated, I know. Alright, a solution of NaOH has a molarity of this. What is its pH, POH, hydrogen concentration, and hydroxide concentration? Okay, well, sodium hydroxide is a base, right? It has an OH, and there's only one OH. So I know that my concentration of OH is 0.0025. And this is 2 sig figs. So if I take this, whoops, I'm going to find my POH by taking the negative log of this. From all those equations you'll have to know, because I don't think they're on the reference chart, unfortunately. So this is 2.6 when you get it. But remember, this is 2 sig figs, so really this needs to be rounded to 2.60. So you have the 2 after the decimal point. Alright, now I want pH, and all I have to do is subtract to find my pH. What the heck? To find my pH, see, my computer doesn't even like pH calculations. So if I just take 14 minus 2.6, I get 11.4, but really I need 2 sig figs. Oh, I wrote it here. This gives me 2 sig figs. And then I just need to calculate my hydrogen concentration. That's a plus. Which is 10 to the negative pH. So my hydrogen concentration is 10 to the negative 11.4, which gives me 3.98 times 10 to the negative 12. And again, I want just 2 sig figs, so this will round, oh my goodness, to that. Okay. Alright, if you can't answer the questions at the beginning of the slides, you know what to do.